Hello to everyone. I hope you are not too tired and can survive one more presentation. First of all, I would like to thank the organizers of this workshop for such a great opportunity to present the work we have done on this challenge. Okay, but before I actually pass to the challenge and our solution, let me first very briefly introduce our company. Therapixel is a French startup based in Paris, which was founded in 2013 by two former medical imaging researchers. In 2015, Therapixel released its first product. It was a visualization software adapted for use inside the operating room. You can manipulate it with your gestures. In 2016, we extend our activity and begin to work on two applications of deep learning to the radiology. Precisely, lung cancer and breast cancer detection. This year, we took the 5th place of the Kaggle Data Science Bowl, which was dedicated to lung cancer detection, and the 1st place on this digital mammography challenge I will be speaking about. We are going to further improve our solutions and commercialize them in the near future. So, I'm passing to the challenge, and first of all, I would like to explain why this problem is a good candidate to be solved by deep learning in end-to-end fashion, from raw data to final diagnosis. Well, first of all, the problem itself, breast cancer, is a dangerous mortal disease. It's a major death factor among women. Unfortunately, it's also widespread. In most countries, there is a regular screening for all women starting from a certain age. This massive screening also creates a lot of data, which are analyzed manually by radiologists. So it would be of great interest, well, both scientific and commercial, to automate at least partially this process. There is another important point, is that the mammography analysis is very standardized. In fact, the radiologists have developed their own language of new visual features, and if you don't know it, basically you are blind. That's how I felt myself when I began to work on this challenge. Basically, it's about learning to see in a completely new world. And by using these new visual features, radiologists have developed rules about how to separate healthy and benign cases from malignant ones. So, in a sense, it reminds us of machine learning. This basically the description of the problem from one hand. From another hand, we have this great technology, deep learning, which has already revolutionized the computer vision. And I put here a slide from the famous ImageNet, just to remind myself and all of us how great it was to have such a big intelligent system for the first time. Okay, so by putting it all together, a reasonable question arises. Can AI improve radiological screening? Okay, so with all this in mind, the DREAM community negotiated the access to a lot of data and launched this digital mammography challenge. The challenge lasted from November last year to June of this year. It included several rounds with intermediate scoring. In total, the organizers gathered 640,000 of images from 87,000 women. Yes, it can seem huge, but in fact, the number of positive examples was not that big, just 1,100s during the first rounds, and later 1,500s in the final validation phase, where we could train on both training and validation subsets. And the test set was used only once in the very end, so overfitting is just not possible. One important point, this data is screening representative sample. So basically it's not where we have very few positives, but we need to detect them, and they can be small, big, so again it's a representative sample. Next. All the images are of a very high resolution. Typically, it's around from 3 to 5,000 pixels in each dimension. And the only information we had to train our models was just the binary labels, 0 or 1, basically, cancer and non-cancer. So the problem was formulated as a classification one. For input, we had last screening images. Usually, we had 2 images per breast, and we had to predict the cancer status within 1 year after the last screening. Yeah. Just a few words about the technical setting. The challenge was entirely in the cloud, and the researchers did not have any access to the data apart from a very small released subset of 500 images. In the cloud, each team had a machine with 22 CPU cores and 2 powerful GPUs. Our training time in the cloud was limited, and we had just 14 days of computation per team and per round. And the metric we were trying to optimize was AUC, area under ROC curve. And I repeat, we did not have any access to the data, so we had to locally implement our algorithms, encapsulate them into a Docker container, and send it to the cloud where it was actually training on the images. Okay, so now a few words about why is this a difficult problem? What is the scientific core difficulties? Well, the cancer itself is a very complex cell-level phenomenon, and it is usually detected by some anomalies, in other words, lesions in the healthy tissue that it creates. In the case of breast cancer, there are 2 main subtypes of lesions. Classifications. Here you can see an example of these bright dots. You can see that it's very fine phenomenon, and that's why we need very high input resolution. Second subtype is mass. Here you can see an example of a rather big mass. So the 2 subtypes lie at a very different space scale. But the real problem is that all these findings can be benign as well. So if you have found a microclassification or a mass, it does not necessarily mean that the patient has cancer. That's why it become difficult, and in fact, radiologists have to be very specific about how exactly these microclassifications cluster, where they are, even what are their individual shapes. In the case of masses, radiologists have to put a lot of attention about size, margin, form, position, etc., etc. All this is important to assess its malignancy. So there is no just one single appearance of the cancer, so just a whole mini zoo, I would say. Okay, so this slide compares the DREAM data to the famous ImageNet common benchmark in general computer vision. So the message here is that the conventional deep learning models, great tools that were developed for ImageNet are not very well suited for this kind of data, for medical images. I would formulate 5 main points. First is resolution. For ImageNet, the most famous architectures you all know, we will train it with rather low input resolution of 224 by 224. For our models, input resolution is approximately 1200 by 800, and in fact it's limited by several factors. Actually, it's several times bigger. Next point is zone of interest, basically the part of the image that defines its label. And in the case of DREAM data, it's about small phenomenon. I would say that less than 1% of the total image surface. And in the case of ImageNet data, it's about big main objects. I would say at least more than 25%. Next point is number of classes, which basically defines the amount of information we have per example. And in the case of ImageNet, it's 1000. In the case of DREAM data, just binary labels 1, 0, 1. Next, the data. The ImageNet is roughly balanced, and DREAM data is highly imbalanced, as you could see. And that's why we have to work with different metrics, which are more complex to work with and to optimize. Yes, and one last point is that human inference time, meaning that how much time a human needs to interpret the image. So an experienced radiologist needs around several minutes to examine the image and to find the anomalies. And to analyze an ImageNet picture, it takes just a fraction of a second. And I think that, by the way, all this stays true in general case when we compare medical imaging data with common visual data from physical world. Okay, so all this being said, and don't forget about cloud restrictions like limited training time. So what do we do? How do we approach this problem? Well, my first reaction when I began to work on this problem was to let's Google for something else, to at least get rid of computational, of the limit on computational time. So I Googled for other publicly available mammography datasets, and I quickly found DDSM. DDSM, in fact, it's an old dataset that contains scanned films. So it's not originally digital as gene data, it's scanned films. And it seems to be the only publicly available dataset that can compete with gene data in terms of positive images. In fact, it's even slightly bigger. It's 1800s versus 1500s. In total number of images, it's much smaller, but the main limitation is usually the number of positive cases. But the most important is that DDSM contains just a plenty of information comparing to just to binary labels of the gene data. Precisely, it contains type of lesions and, most importantly, masks provided by radiologists. So basically, we know where the problem is, where the cancer is developing, as you can see here. So, yeah. So sum everything up, it would be great if we could make use of local information, make use of lesion type from DDSM, but still be able to fine-tune our model on gene, because as you can see, the two datasets are quite visually different. So how to do so? Well, in our approach, we begin by patch model. We resize all the images to the same size of 1200s by 800s. Next, we calculate the center of mass for each lesion using provided masks, and we crop out a patch of, I would say, standard size 224 by 224. Basically, we are trying to reduce the problem to something we know well how to solve. So we do this for all the lesions, and we also enrich this patch dataset by some randomly extracted patches from healthy images. And so this is going to be the input for our model, and we define the output to be 1 out of 5 labels, precisely healthy, calcification benign, mass benign, calcification malignant, and mass malignant. Only the last two cases correspond to cancer. And we put an approximator, a deep neural network in between. Precisely, we start from the VGG architecture. Those of you who are familiar with can still recognize its simple monolithic repetitive pattern. And we are trying to adapt it to our problem. Basically, the goal of our modifications were like following. First, we need to reduce the memory footprint, because next we are going to work on entire images. Second, we are trying to reduce the size of the model and adjust it somehow to work with smaller number of output neurons. Okay. Yes. One important moment, this model is implemented as fully convolutional, meaning that even the last 3 topologically fully connected layers are in fact convolutional. And so once it's trained, I will get back to training a bit later. But once it's trained, we can use one beautiful property of the convolution. We can apply it to an arbitrary input size. And if we apply it to an entire image, we will get a very coarse score map of size 16 by 11 with depth equal to the number of classes 5. We call this patch model the detector net, because basically it slides over the image and it detects, it highlights the lesion. We could have called it cut system, I guess. Okay, so here you can see the highlighted lesion. Now the most critical and tricky moment. How do we pass from patch to image model? Because our final goal is to predict just one single probability if the patient will develop cancer or not. Well, we follow the same scheme basically. We add a final pooling layer and some more processing layers on top of the score map extracted by our detector net. And we train everything end to end. Of course, this part in fact is restored by using the weights pre-trained on patches. So this part is restored using a detector net. Well, in fact, our several first attempts to train this image on entire images failed because the model was either not converging or just memorizing the training set without any generalization. Finally, we came up with several tricks which permitted us to stabilize the training and improve the generalization. And the most important were first, final pool layer needs to have a very large input field, because otherwise, even if the first part, the detector net, has successfully detected a lesion, but at a new spatial position in the validation data, it would not contribute properly to the final label. So final pool down samples even stronger this already very coarse score model. Next important moment was to adjust learning rate. It has to be much smaller on images. And finally, we had a linear shortcut, like residual connection, which basically links the output of final pool layer directly to the final output of the network. This linear shortcut helps to stabilize the training in the very beginning. To give you an idea of training time, it takes around 1 hour and 4 titanings to train the detector net, and around 10 hours to fine-tune it on entire images. Okay, so a little bit about training procedure. Well, in fact, I partially explained it, just to repeat the most important steps. So first, we train detector net on patches from scratch using Adam optimizer with default settings. Basically, the statement of problem is very close to ImageNet, and we know how to do it. Next, we restore detector net weights, and it was also important to restore Adam variables, and we fine-tune it on images with small learning rate. Up to now, we were working, in fact, on DDSM locally. So the next step is to encapsulate it inside a Docker container, send it to the cloud, and use it as a starting point to train on the dream data. Using basically the same setting, Adam optimizer and small learning rate. We also keep track of exponential moving averages. Moving averages are just smoothed over iterations, versions of all the parameters of our model. And they usually perform better than just one best single snapshot. So the last step was to restore exponential moving averages and fine-tune a little bit with stochastic gradient descent and small learning rate. Here you can see an example of learning of how the training was decreasing and how the IUC on the validation set is increasing. So the model is quite stable. Okay, a few words about the data pre-processing. Well, it's very important how you prepare the data. We trained our model on balanced batches, basically batches containing the same amount of each class examples. That was our simple trick to indirectly optimize IUC. So in a way, we hide the true data distribution from our model and are just trying to train it to distinguish between two classes without taking into account the prior probability. Next point, in our approach, the data augmentation plays a crucial role. Both patches and images undergo a very aggressive data augmentation, consisting of both horizontal and vertical flips, rotation for a random angle, zooming, shielding, channel shift. So it was pretty important, and in fact, by increasing data augmentation, I had the impression that we are better covering the distribution of our regions, and we improve again our results. Yeah. Interestingly enough, data augmentation also helps during the inference. In our approach, we take the image, and we calculate, we push it through the network. The original image, it's horizontally flipped version, vertical flipped version, and a version of flipped horizontal and vertical both. And this simple technique, strangely enough, gave us 1% of improvement in terms of RNA. Okay, so now I will show you some results of this challenge. The ensemble of several best models was tested after the end of the challenge on a big screening representative sample. Here you can see basically histograms of sensitivity and specificity distributions among the radiologists. And here you can see, well, clinically acceptable range. Well, our model, of course, gives us the probability, so we need to threshold it at some point in order to compare with the radiologist. So if we threshold it at median value, our performance falls outside the acceptable range. However, if we threshold the predictions of our models at lower bound for sensitivity, we also fall on the lower bound of specificity. Yeah. So, in other words, our models, how to say, are already performing as a clinically acceptable radiologist. In fact, there is also a big issue about fair comparison with humans. In short, radiologists are not evaluated in the same way as our algorithms, and some of their mistakes just stay unnoticed. Okay. So a little bit about our results. These are our curves, our current curves we get on DDSM per breast and per patient level. Since the end of the challenge, we improved our results by approximately 2%. There is still this gap to average human performance. We are currently negotiating to have much more data, and we hope that it will help us to close this gap. Okay, some visualization of our network. It was argued that the problem of breast cancer detection should be formulated as a detection problem and not as a classification one. I agree that it would be much easier to work with, and probably would have better results if we had like locally annotated images, but well, it's usually very expensive and we do not always have this information. But I would like just to show that even using this classification model, we can still get kind of a weak localization of the lesion. So let us suppose that our model tells us that there is a cancer, so label 1. How can we get information about where it is? Well, we can just calculate the gradient of the neuron 1 with respect to the input, so-called saliency map. In other words, we are just asking our model how each pixel influenced the decision. And if we slightly post-process this saliency map, we'll get this. In green area are masks suggested by a radiologist, and this cloud of red dots are slightly post-processed saliency maps. And you can see that here, for example, it seems to me that the radiologist has like very largely outlined the lesion because the model points on just one cluster. On the second case, well, the two, I would say, correspond pretty well. All the dots fall inside the mask. The same for the dream data. Of course, I don't have masks for this case, but the good news is that here we have the same view of the same breast, and the model highlighted the same lesion. And I also have a feedback from one radiologist who confirmed it, that he would concentrate his effort on this lesion, the most suspicious one. Okay, to conclude, deep learning works on complex medical data, even in end-to-end fashion, basically, when we learn to take the final decision from raw data. Sometimes it can demand adjustments, like in our model we had to develop this custom training procedure and to adjust the architecture. However, sometimes it can work almost out of the box. The second place solution for this challenge was based on faster CNN with just minor modifications. It already gives us comparable to human performance, and we hope that we can improve our results by gathering just more data. Also, a new paradigm of data challenge. The data challenges was tested completely in the cloud when you do not have access to the data. but in this way, a much larger audience can participate. And our main goal now in Therapixel is to improve our model, close this gap to human performance, and make a good product out of it. So before I finish, I would just like to say that we will soon open 2 research positions for deep learning specialists, and if you're interested in what we are doing, please don't hesitate to send us your CV. Thanks. If you have any questions, I'll be happy to answer.